Right, I think it's almost settled now at 157 at the moment, 158, so it still goes up. But I'd like to welcome you to another session of Dr. Andrew French's computational challenge sessions. So I hope you've had a go at some activity and not sort of waiting for some sort of starting moment. Each week you want to do a small amount of stuff. You don't want to sort of feel, oh, I must cover the whole of the course that was covered in the hour. You want to do some bits so that you feel you're engaged with it. And there are these little homework things. We're not marking the homework, we couldn't manage that, but there are sort of points which, there are stages which help you to grasp these ideas and what's going on. So I hope you have a go at those. You know, do small bits. Doing nothing is hopeless. Doing something is fantastic, and doing lots is rather exclusive. So do some stuff, engage with this, because that's what it's about. It's not there to like a lecture on astrophysics. This is all entertainment and sounds super. This you have to sort of come out feeling you can do things. Okay, so thank you very much. I will just remind those who are here and point out again and again, next week it'll be between 6 and 7 o'clock. We've had to move it earlier by a bit. So 6 till 7 o'clock next Thursday evening, and then we'll be back to the usual time after that. So there'll be reminders that'll be on the BPHO front page saying about the time. So without further ado, there's nothing else I don't think Nina is there. Without further ado, Dr. French, if you'd like to take it away.
Thank you very much, Robin. Good evening, everybody. So excellent, nearly 200, it's rising, good stuff. Okay, so this is number 3 of the BFO Computational Challenge. Welcome, this is if your first time, very welcome indeed. So all of these talks should be pretty much standalone. We will refer a little bit to what's happened before, but if this is your first one, don't worry, you've not really missed out on anything, although it would be great if you can actually look at the previous videos, which will be available on the BFO website as we go. So last time we were looking at a pipeline of taking experimental data. We used a pendulum, the swinging pendulum as an example. So you've got some experimental data, and how do you analyze it? How do you show that an equation, if you like, which predicts maybe the period of a pendulum from its length, how do you show that that actually matches what reality says? And this is a rather deep philosophical statement, but I think that reality arbitrates what we do. I think reality is real, all right? And we get to see a glimpse of reality when we make measurements in science. So how do we know that our predictions are on the right track? We can never actually prove anything in science. It's not like in maths that we can make axioms and then we can use logic to work out Pythagoras' theorem or something like that. But we can show things that correlate to very high precision. So what do these things mean? How can we actually work this stuff out? So this is actually vitally important in figuring out, how we know what we know. And the sort of fundamental tool for this is the plotting of straight lines and seeing how data fits a straight line. So last time we've kind of used Excel and its little magic recipes to do lines of best fit. Okay, I'm just going to go and add a slide here. All right, so I was going to move that out of the way. There we are. So there's 2 lines of best fits here. We can have a y equals mx plus c fit. So in other words, where we're not really sure, or we do know what the intercept of the y-axis is going to be. So when x is 0, what c is, that's a quantity we want to figure out. And we also want to figure out the gradient, m. So in general, we can get 2 numbers out of a line of best fit. So if our model, if we rearrange the algebra to give us a straight line graph, and it fits really well, then we can be pretty certain that our model is on the right track. In addition, we can get 2 parameters of this model, the m and the c, from the gradient and the y-intercept. So if in this particular thing here, again, we're going to be very general here. I'm not really this is going to be kind of a maths talk, a sort of tool talk, if you like, rather than a sort of a physics example talk. So I hope that's okay. And particularly, I know if you're in the lower 6th and you're studying maths, you're probably doing this about now, I reckon. Certainly the guys from Winchester are. So hopefully this is another bite of the mathematical cherry for you. This particular graph is y equals minus 4.14x plus 5.62. In fact, we can even do better than that. We can show the errors in the gradient and the errors in the intercept. In this case, it's 0.08 plus or minus and 0.56 plus or minus for C. Now that's really interesting because the lines of best fit we can draw, the sort of steepest and the least steep, will tell us something else as well. So we can work out the errors in our gradients. And if our gradients give us something useful, like, I don't know, the measurement of G, which we did last time, you know, the strength of gravity, that will give us the error in our measurement of gravity. So if we're using a graph to predict something important, then we can actually, from that, the possible lines we can draw, we can work out the error in that. Now, we don't have to do that just by eye. We can actually compute this based on the statistics of the data. So in fact, everything on these graphs is automatically computed. And you probably can tell from the styling of it that this is a MATLAB fest, and you can do something very similar in Python. But we're going to start with doing this in Excel. And I'm going to sort of just talk briefly about the recipe, but really it's we're going to kind of get stuck in and do this ourselves. So if you are able, you want to download some files. So before we kind of move on, I want to make sure you've got access to all the data here. So Professor Hughes has sent you an email, or you will have received an email from BFO today with a web link, possibly to a sort of Google Docs. And you want to download the zip file for today's session. If you extract that somewhere on your computer, you'll get something which looks a bit like this. So hopefully all the files from lines of best fit, this directory, will be here. And what you want is the Excel examples folder. And so we're going to literally look at two of these, the y equals mx plus c raw data, and then the y equals mx raw data if we get going. All right, this is the one that we want to see, and this is what it looks like in Excel. So if you can try and load that up, I'm sure my lovely moderators will help if you're having problems. There is an additional way to get this if for whatever reason the Google Docs don't work. You can go onto my website, which is this. I'll put the link in the chat as well. Where is the chat on this one? The chat, there we go. It's coming in the chat. Right. Oh, brilliant. You've got the resources already there. So try the first link first. If that doesn't work, you can click on the link below. And it's this sort of things that look like the little red tents, where the third one down, click on that and you'll get to the same zip file. So can you give that a go and see if you can open up the Excel sheet? Awesome. Right, okay, so I think what we'll do is we'll just actually do that. We'll plot the data and we'll use Excel's magic methods first to get a sense of what's going on. And then we're going to actually work out how to do it ourselves. And then we've got a recipe which we can adapt and use and program up ourselves, and also will give us understanding of actually what's going on. Okay, so and there's quite a lot of you, in fact 214 now, so I can't really ask you if you're having any trouble bringing this up. So I'm going to assume that you can do this, and if not, enjoy the process. This will be videoed after all. So what have we got? We've got some data here. Let's just say we've done an experiment, like our pendulum. We plotted the square of the period versus the length of the pendulum. All right, so from the model we looked at last week, that should be a straight line. So let's have a look. So we've got all this data here. So the first thing we might want to do is plot y versus x. There we go. So let's go. So what we do, your Excel might be slightly different. You might not be using Excel. So what we want to do is add a scatter graph. So in Excel, the Insert tab up here, and you want to pick the scatter graph. Okay, basically every other graph is kind of pretty but useless, really, unfortunately. So scatter graph is really the one we want to use. So we click on that. All right, we should just get a nice blank box. Sometimes it gets clever and might try and make a scatter graph of all the data you've got. If that's the case, just get rid of it. So you right click and you go to select data. So it's fairly intuitive with this sort of menu system. Right, so I've got nothing at the moment. If you've got things here, you can get rid of options just by deleting them. Now what we're going to do is we're going to click the add button, and we'll call this, I don't know, best fit or something, y versus x data. And what we do is we click on this little box here with the red arrow on it, and then we're going to select our X data. So we're going to drag all the way here. And you notice in the box it says A6 to A16, lots of exclamation marks and dollars. All right, that means a particular cell. So we drag them all the way down. There's quite a few data points. Okay, and we're going to do the same for the Y values. So we drag those down. There we are. And then if we click OK, we should have this sort of splodge graph that's now appeared. Now, Excel's defaults are really awful, so we want to change those. So there's lots of ways of doing this. I think if you click and you've got new Excel, you might have something in the top corner where you can modify things. Often the best option is just right-clicking on it and then seeing what your menu tells you. And if we look at this, it says Format Data Series. So I'm going to change the marker. That's a huge marker. You go to Marker Options, Built In, and make it a cross. Okay, that's a bit better. And maybe let's make, that's all right. I think we'll leave it at that color. Okay, another thing you might want to do is maybe make the graph a little bit nicer looking. So here we could probably go for the grid lines, and we'll go for maybe vertical grid lines, which go for major and minor. That looks a bit more professional. And we do need to have some axes titles, because a graph without titles is just a piece of art. It's a picture. All right. If we want to have physics meaning, we need to tell us, or whoever's reading our work, what those axes mean. So axes titles, well, in this case, we'll go for below and rotated. Given we haven't actually specified, we'll just call it Y versus X. But you know, it will normally have a unit. Last session, if you were there, it was the square on the period versus the length. So that would be t squared in seconds squared and length in meters or something like that. But today we're just going to deal with pure maths. Right. So first thing we can tell, hopefully, is that this is fairly well correlated. It's a positive linear correlation. So what is the line of best fit? Well, it's going to kind of go between those points. So what we do is we right click on the data and we add a trend line. So we click on that and it'll give us all sorts of options because Excel can deal with curves. But really what we want to do is convert our physics, into something which is a straight line graph. That's the kind of toolbox we're talking about today. So it's only the linear one we need. Now we've got some options. The options are these three at the bottom. So we can do a Y equals MX fit if we believe that our model goes through the origin. It's a direct proportion of Y to X. In fact, the best direct proportion, if we're plotting, say, prediction versus measurement, like the period of the pendulum that we predict versus a formula versus what we actually measure. All right, and that will be a Y equals X graph of gradient 1, ideally. So we might, in that case, click that option and set the intercept to be 0. But in this case, we're not going to do that. We're going to have a Y equals MX plus C fit. They are slightly different. So if we click just the last two buttons, and what you'll find is you'll get some numbers up top. I'm just going to make those slightly bigger. So right click again, as we'll be doing a lot today. Let's make that 14 points. So hopefully that's nice and big. And so what we've got a graph which is gradient 1.2985. I'm not sure you can change the number of significant figures there. And the y-intercept is minus 0.3901. If you notice, we've now got a number called an R-squared value. And if you've been doing this in maths recently, you'll know that's the square of the product moment correlation coefficient. It's a big word. And basically, what it says is if that number is 1, our data, all of it lies on the line of best fit. So we've got an absolutely perfect spot-on correlation, no ambiguities at all. And it's quite nice when you do an experiment where it's very close to 1. I think only the data I've got that actually does that is the solar system data with the planets. We're doing Kepler-3. In this case, I've deliberately derived this data so it's not brilliantly correlated. All right, so there's to be some ambiguity here about whether this is the right model. What that will mean is that our steepest and least steep lines of best fit will actually be visible on the graph, which is kind of good for our example. But you might find that the errors in your gradient, Excel can't do this, by the way. We're going to have to code that ourselves, are so small that we can't see them. So I've deliberately chosen some data with a bit of a bit of wiggle room. You know, this is like astronomical data or something like that. Okay, so in some ways you could just say, well, this is the Excel model. Why do I need to know how this magic box works? But I'm hoping, particularly all of you are physicists, you're going to be like, hang on a minute, you know, what is this magic? How can we do this? So let's go and find out. And what does it mean? Okay, and that's actually almost a joke, because means are exactly what we're going to be talking about for quite a lot of this. Right, I'm going to leave this one here because we are going to we're going to use this data again, but we'll create another graph from scratch. So what I'm going to do is, in fact, rather than go literally from the beginning, I think that's about the right size. We'll copy this, so we'll Control C, and then we'll paste another graph. So in other words, this can be like our solution, and so that we can check that we're right. I'm just going to move the legend, format legend, and let's make it put at the bottom so we can actually see a bit more room. There we go. That's not too bad. Let's do that again for this one. So right click, format legend, bottom. There we go. Right. So, and I'm going to for this one, I'm going to get rid of the line of best fit. Just literally clicking on it and pressing delete. You'll notice that the equation will disappear. Right. So let's just sort of think what's going on here, and the hint might be what these extra columns are all about. So we're going to go back to the presentation now, and there it is. Okay, so right, maths time. I'll go through this nice and slowly if you've not seen this before. Right, gosh, onslaught. What does this mean? So this is literally your recipe card for lines of best fit. This is what's going on underneath the bonnet of the Excel box that does these calculations. And the nice thing is, once you've coded it up once, you can use it again and again and again. So the spreadsheet you're going to create, you can use for any data. You just need to cut and copy and paste it into your spreadsheet. So what we're going to do is just have a look at what these things mean. So these are literally the means. So X bar means the sum of all of the X values. That sigma sign means just sum all the values over a little index. So X1 plus X2 plus X3 all the way up to Xn, which in our case, I can't remember how many n values we've got, maybe a few hundred, something like that. And then we're going to divide by the total number. All right, so that's the mean average of our X values. By very, very similar notation, that's the mean value of all our Y values. Okay, and this one is the mean value of our X squared values. This one here is the mean value of our Y squared values. And this one, which is one you might not be familiar with, but hopefully the notation works, is the mean value of the product of the X and the Y values. All right, and it should become clear later on why we want to do that. So these are our sort of averages. Okay, so I think what we'll do is actually we'll evaluate those, and then I'll explain why we want to do that. Okay, so let's go and evaluate all those means. So let's go back to our spreadsheet. And so what we want to do is work out, so let's firstly work out the number of our data points. That might be quite handy. I think there's an Excel option for this, but let's just do it manually. If we drag a box over all the way down, and if you notice, if you look at the bottom of the screen, I should have, that's interesting, I actually got 420. Yes, I do. So 420 data points is what I've got. I'm pretty sure that's right. Yeah. So just type 420 there. Okay, so X squared. So what we're going to do is we're going to calculate the X squareds, the XYs, and then we're going to work out the means of this column, this column, this column, this column, and this column using these values here. All right, so what we'll do first is do the X squareds. So equals, actually, let's do the mean first so you can see what's going on here. So X bar is going to be the average of all of these, which is basically the sum. So let's just keep it really sort of structural. We've got the n for here, so that's going to be equals sum. And we're going to go from this cell here, A6, all the way, dragging it down to A425, like that. Okay, the average command will also do this, but we also need to divide it by this one, so that's going to be M2. So /M2. So it's the sum of A6 to A425. That's going to sum all of those, and we're going to divide by the total number of our data points, which is this one. There we go. We've got 4.961 as our mean value of X. Right, now actually, we can be really snazzy about this. I've deliberately put these in order. So if we were to drag this around, it will do the average of all of these. But to make sure that it doesn't go wrong, we need to use this cell and this cell alone. So what we need to do is put a dollar before the M and a dollar before the 2. So what Excel will do, if we drag these down, so if we actually drag these across, you notice at the bottom of the square, the cursor turns from this sort of nice cross to a little black cross. And if we drag it across like that, okay, we'll get some zeros. So Y bar, all right, is now the sum of B6 to B425 over $M, $2. If we didn't have the dollar there, it would increment the M's, and then we'd use this, would be 0, we'd have a problem. X squared bar, we haven't done that yet, that's column C, all right. Y squared bar, that's now D. XY bar, that's now column E. So you can do some really rapid repeated calculations by dragging down and dragging across and replicating these formulae. Very powerful. So we've done these two. We need to do these two. So we need to actually work out what these are. So what we do is we click in the cell and a formula. So any formula Excel, we need to have an equal sign before it. And that's going to be what it was. So A6 and hat, which is a square, 2. All right. And let's do the y squared. Let's actually just drag that across. So the y squared one is B6 hat 2. Don't forget the equal sign. And then if we look at the black square in the bottom, if we double click on that, and we're lucky, it will replicate that all the way down. So if you've got thousands and thousands of cells, you don't want to be scrolling that down. I mean, you could just drag it down like this, but this is really useful. Okay, so I've got quite a lot of data points, but not a ridiculous number of data points. Right, so let's do XY. So we click in there, equals. We've got this one here, A6, and then we're going to use the star, which is computer speak for multiply. And we're going to multiply it. So A equals A6 times B6. Press return. And double click on our little black square at the bottom. And there we go. So now we should have X bar, the mean of the X's, Y bar, the mean of the Y's, the mean of the X squareds, the mean of the Y squareds, and the mean of the XYs. All right, so all the statistical heavy lifting we've basically done now. Right, let's go back. So how does that help us make our line of best fit, you may ask? Right, well, let's go back to our recipe. What does it tell us to do? Okay, just going to quickly check. Cool, 211, nice. Right, okay, so let's go back to this. Right, so the next line, we've got these things, these V's, these stand for the variance. So this is a measure of the sort of dispersion of the data, how the data varies from the mean. All right, so last time, well, 2 sessions ago, we were talking about errors, and we're talking about standard deviations and how our measurements vary from our mean measurements. Well, this is a measure of doing that. So we're going to look at the mean of the squareds minus the square of the means. We'll do the same for y. And then we've got something called a covariance, which is going to be the mean of the xy's minus the product of the means of the x and y's. Okay, so it looks a bit odd because I can't really see the multiplication sign there, but that's x bar times y bar. That's what that means. Right, so let's go and do that straight away, shall we? So let's work out our variance. So there we go. In fact, what would be nice, maybe if we actually do a little screenshot and put that. We could use the snipping tool, but I think I might just add a little screenshot to this one. Right, so let's do that. So let's just do print screen. And I've got a little tool called Irfan View, which I can deposit my screen prints. So there we go. There's the recipe. And I'm going to pop that in there. Oh, that's wet MX. I'm in the wrong place. MX plus C, that's what we want. Let's try that again. Print screen. Go into Irfan View. Oops, no, that didn't work. Let's try that again. There we go. Right, perfect. So I'm going to put that into Excel. And a bit like last time, it's quite nice to have a little picture to remind us what we're doing. All right, if we're going between screens, there is a chance that we might make some mistakes here. So I'm going to leave that at the bottom, just make sure that's visible. Right, so there's our recipe book, our recipe card. Well, we haven't proved why this works yet, but we're just going to use it. Right, so we need the variance. So the variance is going to be the mean of the x squareds. So that's going to be equals the mean of the x squareds. That's going to be n6 minus the square of the x, the mean. So the square of the means. That's going to be L6, and we're going to square that like so. 12.242. Right, let's do the same for Vy. So equals the mean of the y squareds, which is going to be this one. And we're going to take away from that the mean of the y's squared. So this one, and we're going to square it. 24.7 roughly. Lastly, the covariance we're going to do equals the mean of the xy's, this one, minus the product of these two. There we go. So it's going to be the covariance, this one, the mean of the xy's, this one here, and then the product of these ones. Now notice it's a really good idea to actually do these in bits, all right? It's quite obvious from visually what we've done here. And these calculations are not too hard. They build, right? So this one's variance is quite a simple one to check. If you did, you could do this in one mega uber formula, but there's chances of you getting something wrong there are quite high. And in Excel, it's not like in a programming language, it's all relative to cell references. So I'd recommend you space out your spreadsheet and make your calculations really visual so you can check them. Right, okay, so let's go a bit further on. Now, here's the magic recipe. So according to the line of best fit, all right, our gradient M is the covariance over the variance, all right? So the ratio of these things we've calculated. And the C value is, well, y bar, x bar are on the line of best fit. So C is y bar minus mx bar. So let's put those in. Again, we'll prove these in a moment. So M, in this case, is the covariance. So that one, let's pick from there, and we're going to divide that by the variance, which is variance in x, by the way. So our M is 1.299. And our C is going to be y bar minus our gradient, so that one, multiplied by x bar, which is this one here. All right, so minus 0.390. How close are we? Shall we see? Look at that, 1.299. Hooray! And the C value is minus 0.390. Result. Okay. Okay, so there we are. We take our time. So at the moment, we've achieved what Excel does. So we need to do a bit better than that. And we're going to find not R squared, but R. So if we had a negative correlation, R would be negative.
Andrew, sorry. We have a couple of questions about the covariance and what does it mean and how exactly do you get it. Could you very quickly go over that again?
Yeah, sure. Well, I mean, I've left this slightly mysterious because we haven't proved any of this yet. I thought it would be a good idea to do it in a sort of practical way, so we've got something to sort of hang our ideas off. If we go back to just the definitions of what these are, so I haven't shown you yet why they work in our recipe, but we've defined what they are. So if you go back to our presentation, so hopefully the means, or the top line, makes sense. We're doing means of x's, y's, or x squareds, or y squared, or xy's. And so we're defining this thing called a variance, the square root of which gives us our standard deviation. So it's a measure of the sort of deviation of our data from the mean on average. So if you get the idea of a variance being that, and then we can apply the variance to y's as well, the covariance is just the difference between the means of the products and the product of the means. Okay, we can interpret that a bit more by plotting things, plotting x and y, and seeing how they are correlated. All right, you'll find that if they are totally correlated, then this will be 0. Okay, which kind of makes sense. But we'll explore why that works with our recipe shortly. Okay, so think about it at the moment as a type of variance. It's following the rules that we've had here. Right, let's go back to our data set. So happy days so far, but let's just implement this lot. So our recipe says that the covariance over the square root of the product of the variances is R. So let's go and do that. So it's the covariance divided by SQRT, that's the square root, and we're going to have the multiplication of our variances, but it's both X and Y, all right? I'll show you why in a minute. So R6 times S6, okay? Don't forget the bracket because SQRT is our square root function. So T6, that's going to be our covariance divided by the square root of R6 times S6. Press return. And it's not a bad idea to work out R squared because that's what Excel does. So we'll do that. L9 and little hat 2. So 0.836, 0.836, if we have the right number of significant figures. Hooray! So all good so far. So we've just about done Excel, and what would be quite nice to actually plot our line of best fit. So if we just drag this recipe card out of the way, we put it over there. In fact, we can cover up the other one because we know it's right. What would be nice to work out X fit and Y fit. We've got loads of data, so let's make X fit the same values as our X data. So X equals this column here, A6. All right. Okay. Right. Please see the Excel formula again. Okay. I think if there's a particular formula you want to see, if perhaps via the moderator they can put that in the chat, I can go back to that if you need it. All right, so XFit is just going to be A6, and then what we're going to do is do the double click thing and replicate this down. So it's exactly the same as column X. Now our Y fit, we're going to be using Y equals MX plus C, using these M's. So that's going to equal M, which is this one, 09, but don't forget, we need a dollar because it's going to be that cell and that cell alone. So $O, $9. So anything we want to refer to that's a constant, we need dollars in front of the column and the row. Right, that's going to multiply by the X value, which is F6. And we're going to add our C, which is P9, this one. Okay, if you're not sure what it is by reading, just click on it and it will tell you there. But we'll need to put the dollars in. So many dollars today. I'm not being paid for this, but we have plenty of dollars in the spreadsheet. Okay, so $O, $9 times F6 plus $P, $9. That's going to be Y equals MX plus C. Press return. And then if we double click on that again. Right, so now we're going to need Y minus Y fixed squared. What does that mean? That's going to be the squared deviations of our line of best fit from what we actually have. So let's just go and work those out. So that will be equals, open brackets, our Y values, this one, minus our line of best fit values, this one, and then we're going to square it. Okay, that's going to be useful in a moment. Okay. Right, so before we carry on, let's go and plot our line of best fit and see if it matches this one. So it should do because we've worked out the right gradient. So what we do is we right click on this and select data. And now we're going to add another graph. So if we add this, we'll call this line of best fit, LOBF. Right, the X values are going to be Y fit, these ones, all the way down to the bottom. Okay, and our Y values are going to be all the way down to the bottom here. Give time, good. Right, there we go. Look, we've got this big splodge with Excel's horrible inputs. So right click on this, format data series, get rid of the marker. So marker options, none. I'm making a nice line. It's a line style, I think. Let's have line width of 1. I thought we've got rid of the marker. Line color, solid line. Let's have a nice fat black line or something. Oh dear. Oh, right. I've got the wrong data points. Sorry. Control Z. There we are. Control Z is undo. So I need to actually click on the actual trend line data. Format data series. So get rid of the marker. None. Line color, solid line. Nice red one will do. There you go. So hopefully you can see it's the same one. Maybe if I give it a title. So design layout. We are axes titles. Sorry, chart title above chart. there we go. So go for y versus x. Let's call it a y equals mx plus c bit. Brilliant. And in fact, we could probably use slightly better than that. We could put the numbers in, couldn't we? So we could say m equals, what is m equals 1.299, and c equals minus 0.390. Hooray. Right, let's do that. Can I make that a bit bigger? Nah, doesn't seem to like it. Oh, maybe it does. No, oh, I can't do that. Oh well. Right, there we are. So that's our line of best fit. That's better. That's nice, isn't it? All right, so there we go. So we've achieved what Excel has, and we know all the parameters. What we don't yet know is the error in this, and the steepest and the not so steep graph. So I think at this point, let's go back and figure out what's going on here. All right. So if we go back to our Excel sheets, I'll explain this recipe shortly. So here we go. Let's make this nice and big. So what are we actually trying to achieve here? Imagine we've got a straight line, all right, and these these vertical lines go to our data points. So we'd really like to have a line which minimizes the deviations from our data points to our line. Now, if we just sort of add up the deviations, all right, the negative ones will probably cancel with the positive ones, and that won't be such a good idea. So what we do is we look at the deviations and we square those and we add them up. So this is what we just calculated earlier, this sum of squared deviations. So what we're going to do, so this is y minus mx minus c. All right, that's our line of best fit. I'm going to take that away from our actual data points and square that. So this is this sort of, we call that sum of squared deviations. Now, if you think about it, although that's a sum of these, it's actually a function which varies with m and c. These are parameters. So although this might be a bit odd to think about, you could imagine a sort of grid of m and c values, a sort of chessboard. And at each point on that chessboard, you can take your data set, work out this sum, and color code it. And if not a chessboard, maybe a sort of surface, all right, of height, which is s. And at a certain m and c value, you've got a minimum of that surface, like a kind of hole, like a sort of pond in a mountain tarn. We want to find out where the mountain tarn is, what coordinates are in my mountain tarn. So that's what we're trying to achieve. All right. So what's our recipe? Well, we've got our law of physics. We're rearranging that to form something that's y equals mx plus c. And we're then going to plot on a graph, work out the line of best fit. We're going to determine the gradient and the vertical intercept c from this line of best fit. And then we're going to try and work out the errors in M and C, and also a measure of the fit, which is our product moment correlation coefficient. So all we've done so far is on everything apart from the errors in M and C, more to come. So in other words, how do we work out the 0.08 and the 0.56? So let's have a look at this. Now we're going to do a bit of maths here. So if you're not in the sixth form and you've not done any calculus, don't worry, hold on to your hats. We will make loads of progress by just applying the rules. But for those of you who are at that place, I think you'll enjoy the next stage because it's applying some basic calculus ideas, but in a slightly unfamiliar way. All right. So just to recap what we're trying to achieve. So we want to plot this versus M and C. Now I've used the not quite the same data set that we had before. This is a negative correlation, but there we go. And just to make it a bit easier to see, it may not sound like it's easy, but I've taken the minus logarithm of that. All right, why have I done that? Well, you can see the variations a bit more because it's a log. I've minused it, so I turn a trough into a hill. And it's a bit easier to see a mountain peak than a sort of little hole, and you'll just see the sides. And so this is the three-dimensional plot. So it's a 3D plot of the minus log of this lot versus M and C. And we can clearly see that where that purple star is, there's a sort of optimal value. Now, if I plot that, if I sort of look down upon the mountain from a sort of drone above, and I color code it like a sort of contour map, then we see that M is just over 5, well, 5.6, and sorry, M is about minus 4.14, this is M, and C is about 5.6, are this maximum. All right, so they're the M and the C values we want. So do we have to go and plot a complicated graph? Is this what Excel is doing? No. No, we can get there much with some very simple calculations that we've just done, in fact. So, but for that, we need to do some calculus. Right, hold on to your hats. So here's the thing we want, and I'm going to invite you to just look at this side first. All right, this is a bit much. Cover the other side over with a piece of paper. So what we're going to do, we're going to work out the gradient of this function, the slope of it, with respect to variable m. So what do we do? Well, this is a series, you know, so it's this term and then the next term with little values of I, you know, I1, I2, I3, etc. But so because we're like, if you differentiated x squared plus x cubed, you get 2x plus 3x squared. So this fact that we've got a sum there, it doesn't matter. We can differentiate this bit here, but it's got a square. So we bring down the square, we make that look like it's you know, x squared, and then we differentiate the bit in the brackets. All right, that's called that's the chain rule. So we write that down, and the coefficient of m is minus xi. Now this sounds weird, doesn't it? For your x to be the coefficient, but it doesn't matter. You know, we've got our variable is m. So although x is what we normally associate with a variable, in this case it's just what we multiply in front. But remember, each part of our sum has a different xi value, so we've got to make sure our xi is within that sum. Right, now when we are at our peak of this, or if we're just looking at s, our base of our peak, the gradient of that is 0. In fact, the gradient of that is 0 in the n direction and in the c direction, right? In fact, every direction. So these things cause a partial derivative. What does it mean? It means find the gradient, assuming everything else is a constant. So we can ignore the yi's, that appears like a constant. Whereas on this case, sorry, the c's. In this case, we ignore the m's. So if ds by dm, this partial, it's basically a small change in s over a small change in m, as that small change goes to 0. If that's 0, if you have a look at this, we can get rid of the 2's, and we can get rid of the minus 1's, multiply that out, and if you think about it, it's the sum of the xy's minus m times the sum of the x squareds minus c times the sum of the x's. All right. So if we divide that all by n, what have we got? We've got, that's the top row here, all right? We've got xy bar minus mx squared bar minus c x bar, all right? So that's why we were doing this, well, we haven't got to the covariance yet, but that's why we're doing the means of the xy's. Right, let's do the s's with respect to c now. A bit of an easier one, this, because the coefficient of c is minus 1. So we differentiate this, we find the gradient, we set it to 0, we get rid of the minus 1 and the 2, and then we've got the sum of the y's minus m times the sum of the x's minus c times the, well, sum of 1's, which is n. So if we divide that by n, what have we got? We've got the mean value of y minus m times the mean value of x minus c is 0. Or y equals y bar is mx bar plus c. So we know that the average value of x and y must be on our line of best fit. We've proved it. All right, there's no ambiguity about that, because this is maths. So there we are. So we proved this, and now we know what c is in terms of m, so we can substitute that in this equation. So we're replacing c by this one here. So that's in the brackets. So another good tip when you're doing maths like this, and you're substituting, brackets are your friend. So before we rearrange, make sure your substitution is there and clear. And then another stage, you can then tidy it up. All right, that's a really, really useful tip to prevent algebraic embarrassment. Yes, thought is expensive, ink is cheap, particularly if you're using a computer-based surface. So what we can do is we want m. So if we write m down and we go through our expression and pick out the terms, we've got a minus x bar. In fact, there's an x bar squared. There we are. We've got a minus x squared bar here. And then what have we got left? We've got the xy bars minus y bar times x bar. So if we rearrange that, we've got this lot here. And the top one is the covariance. And the bottom one is the variance. So we're done. So there we go. That's how we worked out our line of best fit. So how did we work out our, just make sure we got that. Any questions have popped up? This might be a good point to ask us some questions. Nope. Okay. All right.
Sorry. Yeah, there's a couple of questions in the Q&A box, if you could go through it.
Sure. Yeah, no problem. Right, because I think we've done that. Yeah, so the R and the R squared. So yeah, so the R is the covariance. Well, we'll get to that bit actually. Would it make a difference if the data point variance was calculated perpendicular to the line of best fit? Yes, I think there is. So yeah, if you go on to something like Math World, there are slightly different ways of doing this. All right, so we're going to be comparing a Y correlation to an a Y deviation to an X deviation. That's going to be in our derivation of R. There are slightly other ways of doing this. You could do a say perpendicular to the line, but this is the most common. How did you calculate the covariance? Right, well that's so our covariance, remember, is the mean of the XYs minus the product of the means. So before we carry on, let's just go back to our spreadsheet and make sure that we know what that is, because we're going to use that. It's slightly in a different aspect. So there we are. So our covariance, so that was going to be P6, which was the mean of our XYs, this one. And we did that was the sum of this column here divided by 420. And then we're going to subtract from that the product of the X and Y means. Okay, cool. Hope that's all right. Right, so what is this product moment correlation coefficient? Where does this come from? Why is it the formula that it is? Well, if you repeated the same analysis, so this one here, but with the X deviations instead of the Y deviations, well, we'd expect the same thing to happen, the same maths. We could just exchange X and Y. So we'd end up with something that looks like this. If you notice the covariance, doesn't matter which way you have X and Y, all right? Because X times Y is the same as Y times X for numbers, not like matrices, other things. And then in this case, we'd have the variance of Y. Now, so if it was the same line of best fit, it was something like X is big M Y plus D. Okay. X fit is the same as X, by the way. It's exactly the same column as X. If we had the same line of best fit, we just rearrange this. All right. If you think about it, then the gradient big M here is 1 over little m. All right. It's just so if we divide both sides by big M, all right. So we've got Y is 1 over big M minus D over big M. And then we got the sort of the C's, we can compare the constants, but the gradients are big M is 1 over little m. So if our line of best fit was perfect, the product of this one and what we had before would be 1. So, all right, what we can say is, well, let's just look at the square root of that. So the covariance over the square root of Vx, Vy is ideally 1. But in fact, because we've done the square root and we've got the covariance here, if X and Y are anti-correlated, all right, so this thing here is negative, then that gives us a nice negative sign and shows us we've got a negative correlation. That would be really useful in a kind of machine learning situation where you have to tell a computer, is this a positive or negative correlation? Or you can just look at the sign of this. So there we go. That's by looking at the X or the Y deviations, working out what their gradient should be. The product of them should be 1. So if we work out the square root of that, and that then gives us the sign essentially, we've got this definition for R, or rather kind of the reverse of that really. The R can be negative or positive, and if we square that by multiplying these two things, we should get a positive number. So that's essentially what R squared is M big M. Okay, that's what Excel's doing, but we can do better than that, and we can work out R. Okay, cool. So right, so I think what we'll do is we've got sort of 10 minutes left. There's no open questions. I'm going to give you a little tour of how we can finish the rest of this off. So last part of our recipe is this. Now, I'm not going to prove this. All right, so this is something you can go, so mathworld.wolfram does a bit more analysis, and you can actually work out the errors in M and C based on the variances and this thing called S. So if you have a look at this, this is the sum of the squared deviations that we tried to minimize, but we're dividing it by n-2. Why would we want to do that? Well, in terms of working out these errors, we've already used the mean and the variance. So to make an unbiased estimator, we want to divide by n-2. All right, so That's quite a subtle thing. And it won't make much difference in our case because we had 450 data points. So let's do a quick screenshot of this, print screen. And let's put that into the spreadsheet. And there we go. I can't remember if that's in our original recipe. So let's go and do it. There we are. Oh, it is there. It is there actually. Yes, we don't really need that. Right. So what we want to do is, okay, so we can work out S. So S is going to be the sum of our squared differences. So that's equals sum. And we're going to go for all of these, all the way down to the bottom. Okay. And we need to divide by n minus 2. So divide by this one minus 2. So open brackets, this one minus 2. All right, and then we're going to square root the lot. So SQRT in front, close the brackets, press return, and we've got 2. Right, so now we can use our recipe. So let's, in fact, I think, have I still got it up here? Yeah, let's, that's a bit bigger. So I'm going to put that there. Makes it a bit easier to see. Right, let's pop that out of the way. Right, so it's a bit like cooking this. We're following a recipe. DM, so what do we want? That's equals S divided by SQRT of n, which is this one. And then we're going to multiply that by 1 over the square root of the variance. So open some brackets. We're going to divide that by this SQRT of variance of x, this one. Notice how it's a really good idea to have all these things worked out so you can just point to it. So there we go, that's our 0.028, which actually, yeah, we've got some different data here, we can't tell for that one. And C, let's work it out. So it's going to be S, so this one, divided by root n, SQRT of the number of data points. And then we're going to multiply this, so open brackets, another open bracket, multiplied by the square root of 1 plus the square of the means, so that one squared, and then we're going to divide that, let's put it in brackets just to make sure, divide that by the variance, which is this one. There we go. That's the most complicated formula, so I'll leave that for a few seconds if you're doing this live. Practical definition of S. Well, essentially, so the big S is the thing with is the sum of the squared deviations. So I guess it's a sort of it's a kind of variance in many ways. Sort of, you know, we're looking for the deviation squared from the line of best fit. The n minus 2 is perhaps a little bit more subtle in terms of estimating what that deviation could be for an infinite number of data points. So yes, it's a bit more than just an intermediate step. If you look at the definition, it's an average of those squared deviations, and then we're square rooting that. So it's like a sort of, you know, an average deviation. Okay, right, so there we are, and then we are done. So our final answer would be 1.299 plus or minus 0.028, and our C value is that one plus or minus 0.390. X squared bar, right, okay, well, X squared bar, there you go. So we're summing up all the X squareds, and we're dividing by our M value here, okay? The dollars, because we're fixing that cell, M2. Right, time is ticking, so it'd be nice to actually finish this off, and I'm going to plot the steepest and the least steep graphs. So what we're going to do is the steepest, the lowest, we'll do the lowest one first. So that's going to be y equals mx plus c, but our m is going to be our m here minus this one. Okay, just in the chat, if we had a non-linear model, we make it linear. So we had t versus root L. We say y is t squared and L is x or something like that. All right. Okay, so we can always use this even if our model is not linear. So our lower value is going to be equals. So we're going to have our m, which is this one minus this one here. Don't forget the dollars. All right. Don't forget the dollars. That's our smallest m value. Our x fit, which remember is just x. And then I think what we'll do is we'll have the smallest c value as well. So that's going to be this value of c minus this value of c. And don't forget the dollars too. Don't forget the dollars. Oh, there we are. Brilliant. Okay, so we can replicate those down. Let's just see what it looks like. Let's make that a bit bigger. What we'll do is we'll do right click, select data, and we'll add, and we'll go for line or best fit min. The x values will be all of these x fit ones, all the way to the bottom. And our y fit values are now going to be our lower ones. So we'll see how this works. All right. Okay, we're coming towards the end, so I might just sort of show you the last bit. Right, so if we right click on that, format data series, get rid of the marker, line color, solid line, and maybe make it green or something like that. So you can see there's a small difference because our gradient is actually, you know, it's a very small difference. So there's our line of best fit, there's our green one, all right, which is a little bit lower, all right. Okay, so I think that's probably enough of that. So we've only got a few minutes left. So what I'll do is I'll show you in true Blue Peter style. Here's one I did earlier. So this is the one MX plus C solution. As you can see, it's very similar to what we've just done. In fact, it's identical, I hope. Let's make that slightly bigger so you can see it. So there we go. There's our formula. Let's make that text larger. All right, and you can see the green line. We've also got now an upper line as well. So this one, we're using our m value plus our dm rather than minus dm. So that's our steepest gradient. We've got the c is now our c value plus our error in c, which we figured out. And there we go. We've got our blue line here. Right. So we've not done any programming today. I think maybe in the video I might sort of talk about how you might do this in MATLAB or Python as well. But essentially, we're applying this recipe. And it doesn't matter what your data is. If we want to find a line of best fit, all right, and it's an x versus y problem, we can work out the gradient, all right, we can work out the y-intercept, and for the product moment correlation coefficient, if that's close to magnitude 1, then we know our data matches our model very, very closely. Okay, so a little question, more data X, Y, Z. Oh gosh, well, yes, that's well done. That's an impressive. I'm not going to talk about Graham Schmitz, I'm afraid. this is a basic course. Absolutely. Yeah. So, but yeah, this is the nursery slope, but it's a very powerful technique nonetheless. You should certainly know this for A level, and certainly for first year university, definitely. Right. Okay. So we haven't spoken about how you can do y equals mx. But it's very, very, very similar, the same kind of idea, except now we don't have to worry about c. So in this case, we do our partial derivatives, and our m is xy bar over x squared bar. And everything else is the same, apart from there's an n minus 1 there. So we've only used one parameter. And there we go. So in this case, you'll get, and in fact, I'll just quickly show you the solution for a y equals mx fits. So this one here. So there we go. It's a very, very similar process. In fact, it's slightly less data in this case. And you can see the mean line here, the line of best fit, 1.187x. There's the r squared value. And these are our lower and our upper lines because you've got the m's and the d. Well, there's only one. There's only a gradient here. Our c is perfectly 0. Okay, so if you want to sort of have a really good go at this, what I'd recommend for homework, let's just bring my little spreadsheet in. So the data analysis notes, which have all this stuff in it, problem 1, part 8. So I think about half of the course, the sessions will refer to this problem sheet. The other halves are a kind of make a screencast of what you've learned. I think that'll be a really good way of engaging with the material, you know, rather than just reading through it. But I'll show you what this looks like again. So I think it should be about homework resources. There's actually a note on this as well. If you want to print something out, and it's a bit shorter. It's basically exactly the same as what we've just done, but in 2 pages of color A4. So that might be nice. So the data analysis worksheet is this one. It's got everything we've done the last couple of sessions and a bit more too. And this bit here is what we call linear regression. So this is the recipe that we've just been talking about. All right, everything is there. And so question 1, part 8 is this bit here. And what's quite nice about that is that there's only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 data points. So you can type those into Excel and you can generate this Excel sheet. Or if you want to save time, you could use the Excel sheet you've just done, get rid of the data and just type these ones in. And you should find everything auto-calculates, which would be quite snazzy. And there we go. And if you really want to push it, maybe you can program this slot in Python as a function, taking on board maybe a spreadsheet with this data. So loads of options here of getting to grips with y equals mx plus c or linear regression. So I think we're 2 minutes over. So thank you very much indeed for your participation. Next time, we are going to be applying everything we've learned so far to a practical example. We're going to pretend to be nuclear physicists at the Chernobyl disaster, which happened in Russia about many decades ago. And we're going to analyze some data to work out half-life of one of the radioisotopes. All right, so we're going to put all this stuff into practice. So hopefully that's exciting. And you can come along next time, bring your friends. Thank you.
Thank you very much indeed. In fact, I think you've covered all the questions along with Nina and Anna. So yeah, that's it. So it remains for everyone attending to actually get to grips with this and have a go. You don't have to do everything, but have a go at part of it and see what progress you make. Okay, thank you very much, Andy. So I think we'll leave